So let me start by recalling the theorem that I ended last time with, and just giving a brief idea of how it's proved. Very, very brief. So the theorem was for shift spaces. So we let X be a shift space, and we let L be its language. So L is the collection of all finite words which appear in some element of X. And we assume that there is a decomposition. That is, there exists three collections of words, a collection of prefixes, a collection of good words, and a collection of suffixes, such that any word in the language can be decomposed as a concatenation of a prefix, followed by a good word, followed by a suffix. And if these have the property that first, the collection GM has specification. I recall what this means. GM is the collection of all words for which the prefix has length less than or equal to m, and the suffix also has length less than or equal to m, so it is a uniform distance away from being one of the original good words. And we require each of these to have specification. The gap size, the gluing time tau in specification is allowed to depend on m, but not on anything else. And we also need that the entropy of the prefix-suffix collection, which I remind you is the exponential growth rate of the number of prefixes and suffixes of length n. We require this to be less than the topological entropy of the shift. If these conditions are satisfied, then there exists a unique measure of maximal entropy. So this is the theorem. I stated it. I did not give any examples yet. I think I will defer examples until we have the smooth version, and then I'll give some partially hyperbolic examples. But I want to say a very brief word in just 4 or 5 minutes about how this is proved. So the uniform theorem, the theorem for uniform specification, was proved in 2 steps. The first step is to construct an ergodic Gibbs measure, and then the second step is to prove that that implies uniqueness. And the second half of that is more or less the same here. There's some technicalities that are irritating and unenlightening, and I will not talk about them. What I will mention is that the very first step in the construction of the Gibbs measure is to establish these counting bounds. So the first counting bound yes.
The union over all GM is equal to L.
Yes, the union of all of the GMs is the entire language. So it's useful, at least for me, to think of this as some kind of Pessin decomposition, at least spiritually. So there are 2 counting bounds that you need. You need a lower bound and an upper bound. The lower bound is completely immediate. The argument that I gave for this last time just involves submultiplicativity of this sequence and nothing more. Requires no assumptions on the shift space. The upper bound required the specification property, and therefore a priori we only get the upper bound for the collection of good words. So this specification property implies that the number of good words, yes?
Which one requires the specification property?
The upper bound. So there are 2 sets of uniform bounds. There are counting bounds and there are Gibbs bounds. Yes, Keith? Yes. Yes, so in the counting bounds, the lower one is free, the upper one requires specification. In the Gibbs bounds, the upper one is free once you have the counting bounds, the lower one requires specification. So it's reversed. So the upper bound for the number of words can be obtained in a uniform way if you only count words in GM. Now, a priori, this does not give a uniform upper bound on the number of words in the entire language of length n. And that's precisely where this second condition comes in. That's the computation that I want to show you, and that will essentially, that's the main difference in the proof here. So to illustrate how that goes, let me just be sure, yes. So let me show you the computation. Let me start by just defining a couple quantities. Let P sub I be the number of prefixes of length I divided by e to the I times the topological entropy. And let Si, actually Sk, be the number of suffixes of length k divided by e to the k times topological entropy. Condition number 2 guarantees that both of these series are summable. And that's really the only thing we need it for. This guarantees that the sum of the pi's is less than infinity, and the sum of the sk's is also finite. And that's going to be what we need in the proof. So now let me show the computation. Suppose I count all the words of length n. I fix some value of capital M, which I will take to be large enough that a certain inequality later is satisfied. So I count how many words in the language there are of length n. Well, these come in two sorts. Perhaps they are in GM, so perhaps the prefixes and suffixes are both shorter than m in length. Or perhaps they are not. If they are not, then I have a decomposition of my word of length n into a prefix of length I, a good word of length j, and a suffix of length k, where I, j, and k add up to n. And in addition, either I is bigger than m or k is bigger than m. So the maximum of I and k is greater than m. So this gives me an upper bound, which I can now say something about using the definition of pi, the definition of sk, and the upper bound on the number of good words. So this is less than or equal to, first term is unchanged. I take a sum over the same indices. The number of prefix words of length I is pi times e to the ihx. The number of good words of length j is less than or equal to q naught. So this is the case when m is equal to 0. I'm only counting good words themselves. Times e to the j times entropy. And the number of suffixes is sk times e to the k times entropy. But I plus j plus k is equal to n. So if I multiply this and this and this, I get e to the n times entropy. And e to the n times entropy is less than or equal to the number of words of length n. So I obtain the bound, this is less than, well, let me just write it and then say the next step. The next step is to observe that because both of these series are summable, for every delta greater than 0, there exists an m such that this sum is less than delta, simply because both series are summable. And this quantity, e to the nh, is less than or equal to the number of words of length n. And I conclude that this bound admits this form. And now if I move the delta term to the left-hand side, I obtain the following conclusion, that the number of words of length n which are in GM is at least 1 minus delta of all of the words of length n. So this is another sense in which it's legitimate, I think, to think of this as analogous to a Pessin decomposition, that as you increase m, you pick up more and more of the words. And the proportion goes to 1. And as soon as you have this, you can immediately deduce the uniform upper bound on the number of words of length n, because you simply take delta equal to 1/2 and take an m such that this works, and then you get that the number of words of length n is at most twice the number of good words in GM. And it also gives you a lower bound on the number of good words once m is large enough. And from there, the rest of the proof is essentially the same. The only difference that I will highlight so this gives you, yes?
You have this upper bound, but it's exact exponential, or it's just like...
Exact, so let me write it. Let me write it. So this gives some constant here. So you will get this constant, but as 2 times qm for some sufficient value of m. And there exists m and little a such that the number of good words is like this. And this then is exactly what you need to prove a version of the Gibbs property. So here's the Gibbs property that we get after some argument, which I omit. When you do the standard construction of a measure of maximal entropy, you make the same argument as last time to obtain some kind of Gibbs property, and what you get is that the measure you build has weight on each cylinder, which looks like e to the minus n topological entropy, up to within an upper bound which is universal, and a lower bound which depends on m. So it's not quite a Gibbs bound, not in the classical sense, but it's a non-uniform Gibbs bound, and it turns out that this is enough to run the argument.
Can you say, isn't what how Km depends on m? If you increase m?
Km will it will be sort of directly determined by this Qm. Wait. You can chase these constants, and in the end it probably depends on how the specification time tau depends on m, which a priori you have no control over. Now for a given system you may have some control, and then you could try to do it. From here, the rest of the proof is essentially the same as the uniform case. There are some annoying technicalities. As I say, I don't think you learn anything if I tell you about them, and I don't want to talk about them, so I won't. Instead, we should say something about the non-symbolic setting, because this is where the most interesting examples live, in my mind at least. And I promised a dictionary. So to translate everything into the setting of, say, smooth dynamics, we need a dictionary, and this requires me to recall the following definition. Given 2 points x and y, so now the setting is that x is a compact metric space and f is a continuous map. And if you like, you may think of a uniformly hyperbolic set, a locally maximal hyperbolic set for a diffeomorphism, because that's the first example. The nth dynamical metric is defined by looking at 2 points, taking their orbits of length n, and seeing how far apart those orbits separate. And then the balls in this metric are the Bowen balls. So this is simply the set of y such that the orbit of y remains within epsilon of the orbit of x for n iterates. And now the dictionary from the symbolic case to the smooth case, or I say smooth, I guess, or maybe topological or non-symbolic at any rate, is that anytime we talk about the language and a word in the language, we should now talk about a finite orbit segment. So before, any time I had the language, I now want to talk about x cross n, where a pair, xn, is associated to the first n points in the orbit of x. And if I talk about the cylinder associated to a word in the language, which gives me a subset of my symbolic space, then instead I want to talk about the Bowen ball. And now the game is to take the results from before, the proofs from before, run them through this dictionary and see what else you need in order to make everything work. And what you need really boils down to something which I said very quickly last time, didn't place any emphasis on, and then proceeded past, which is that when we do the proof of ergodicity, there was this step at which I said, well, we have an estimate on this quantity. So I think it was something like this. The lim sup of this is greater than or equal to some constant times the product of the measures of the cylinders. And I said that if you know this, then because you can approximate any measurable set using cylinders, we deduce that the lim sup of the measure of this set admits the same bound. That step requires the fact that cylinders generate the Borel sigma algebra. Well, if I want to do anything in the non-symbolic setting, and I run things through my dictionary, then I need the Bowen balls to generate the Borel sigma algebra. And that's not immediate. For example, if you take an isometry, this is absolutely not true. And I guess I need to be a little more careful. What I need, or what I want at least, is that for some fixed epsilon, the Bowen balls generate the Borel sigma algebra. Of course, if I'm allowed to vary epsilon, then I can do whatever I like. But the point here is that all of the constructions work at a fixed scale. So when I say what specification is, you will see that specification goes by replacing words with orbit segments, cylinders with Bowen balls, and you will shadow to within some fixed scale, and you need to work at multiples of that scale and have everything generate the Borels. So if you look into the details of the proof, which there's a little bit in the notes and I won't get into here, you see that this is really what you need. You need there to be a scale epsilon at which the set of Bowen balls associated to that scale generates the entire Borel sigma algebra. Well, this is exactly the expansivity property. It's not the usual way of stating it, but it's what we need. So let me formulate the property and then explain how we can weaken it a little bit. So what's our definition? Definition is the following. Given a point x and a scale epsilon, define gamma epsilon plus of x to be the set of points y whose orbit stays within epsilon of the orbit of x for all non-negative n. So it's an infinite Bowen ball. It's a Bowen ball of infinite order. And of course, in the setting of a hyperbolic set, this would just be the local stable manifold, right? So if you have a hyperbolic set, this is the local stable manifold. If you have a uniformly expanding map, then this is a single point. And that's the property that's one property that will suffice for this. So if this is equal to a single point for every x, then we say that f is positively expansive at scale epsilon. And this is the appropriate notion for non-invertible maps. If you have a non-invertible map, something which is expanding or non-uniformly expanding, this is the appropriate notion to use. And if this happens, then you exactly get this property that the Bowen balls generate the Borel sets. If you want to study a diffeomorphism, something which is invertible, then, so this is what you should use for non-invertible systems. For invertible systems, you should use the following. You should use the two-sided infinite Bowen ball, which is the set of all points x for which this same thing holds in both forward and backward time. And of course, if I make the same definition but with n less than or equal to 0, then I get gamma epsilon minus, which for a hyperbolic set is the local unstable, and the intersection of those is a single point. So if this two-sided infinite Bowen ball is a single point, then f is expansive. If we really want to distinguish, we may say two-sided expansive, but what's going to actually happen is that anytime I'm explaining a result to you, I'm probably going to use two-sided expansive because that's where my examples live. And anytime I'm explaining a proof, I'm going to use positively expansive because the proofs look simpler. Yes?
So when you look at the invertible system.
This is my next sentence. Those do not generate the Borel sigma algebra. You're right.
Are you going to use two-sided Bowen ball?
Yes, exactly, exactly. So in the two-sided, if you're two-sided expansive, then it's just a little more obnoxious technically. You use two-sided Bowen balls. So probably the most aesthetically pleasing way to do everything in the invertible case would be to make the dynamical metric a two-sided object, to make Bowen balls a two-sided thing. But then you might have to change the definition of entropy a little bit to put a 2n there, and this is not the way we wrote the paper. Instead, there's more fiddling around, but this is what you have to do. So I just want to point out the two different definitions to say that the theorems are either assumption works to get you the theorems. I will explain any proofs in the positively expansive setting because it just looks simpler. Although in fact there's not too much more to say. I think I just want to state the result now, which is, yes. Before I state the result, I should observe first that if you are a locally maximal hyperbolic set for a diffeomorphism, then the map is expansive. And I'm not saying the scale at which it's expansive depends on the scale at which you have a local product structure, and that's it. So that's a standard thing. It just follows from what I said about the local stables and unstables being given by these sets. In order to formulate the general result, and therefore formulate our generalizations of it, I also need to define the specification property. So let me come back to expansivity in a little bit. But for now, let me define the specification property in a non-symbolic setting. which I should do by taking the symbolic definition and running it through this dictionary. So I will give it in a not entirely standard way. We say that a collection G of orbit segments has specification at scale delta. If there exists a gluing time tau such that for every finite sequence of orbit segments in this collection, in the symbolic setting, I asked for a finite sequence of words from the good collection. Now I ask for a finite sequence of orbit segments. I want there to exist times T1, T2, up through Tk, and a point y. So y is to be my shadowing point, and the ti's are to be the times at which it shadows the various orbits. So the picture, before I write the rest of it, maybe I should just draw a bit of a picture, which is that if these are my orbit segments, so that this is x1, this is the end of that orbit segment, this is x2, this is the other end of that orbit segment. You will notice here that I'm drawing a picture that looks as though it belongs in continuous time. They're just easier to draw pictures like this that way, and there is a corresponding continuous time definition. So what you want is a point y, which follows the orbit of x1 to within epsilon, and then follows the orbit of x2. So this is the point on the orbit of y after time t2, and then it should follow the orbit of x2, and then it should come and it should follow all the other orbits in between, and then it should follow the orbit of xk. It will be convenient to write this as, to write S1 for, well, no, I'm getting ahead of myself. So I want two properties to be satisfied here. The first is that I should have this shadowing property. So if I take the iterate of y at time ti, this should lie in the Bowen ball of order ni around the point xi. Delta, delta, delta. Yes. So this is the condition that you shadow each of the orbits in turn. And if you think about the dictionary, this corresponds to lying in the appropriate cylinders in the symbolic case, which is just the condition that the right word appears in the right place. But if this is all we ask for, then you can deduce this from topological transitivity. The extra condition is that you have control over these times, so that if you write Si for Ti plus Ni, so this is just the time at which each of these shadowings ends. Then the time that the next one starts lies within tau of that. So you follow the first orbit segment, and then you can relax for time up to tau. And then you follow the second one, and you can relax for time up to tau, and so on. So the classical specification property as introduced by Bowen looked a little bit different from this. It was stronger in several ways. First, it required this to work for all orbit segments, not just ones from some collection. Second, he actually requires more control over the gluing time instead of letting it be flexible like this. And third, at least at first, I think he asked for it to be a periodic shadowing orbit. But this is enough for the uniqueness results that we get.
Just one comment. For the second question that you mentioned, made the classical definition closer to mixing, right?
Yes. Yes. Yes, that's exactly the correspondence that you should think of. The relationship between fixed time specification and variable time specification is the same as the relationship between mixing and transitivity. Yes. And transitivity, of course, is enough to get uniqueness results. If you want something like Bernoulli or decay of correlations, then you should ask for more. So, this is the specification property. And in order for this to be useful, we should say something about why this holds for locally maximal hyperbolic sets. So if I have a locally maximal hyperbolic set, the claim, well, let me write it this way. I introduced some notation. I should use my notation. If I consider the space of all finite orbit segments that lie in this set, then it has specification at any scale. So if I simply say that a collection of orbit segments has specification and I do not specify a scale, then what I mean is that it has it for every scale. So let me simply draw the cartoon.
And then tau does not depend on delta?
Oh, tau depends on delta. Yes, yes. Tau depends very much on delta. And it will be clear from the proof why. So the core of the proof is just a one-step or two-step shadowing. Suppose I have two orbit segments. So let me consider an orbit segment X, M. Actually, let me do it the other way. Let me call this ym, just for consistency with later notation. And then let me have an orbit segment xn. And I want to find a single orbit which shadows both of these and does not take too long to go between them. So here's a way to do it. I take, remember, I'm assuming that I'm in a locally maximal hyperbolic set. So I take the unstable manifold through the endpoint of the first orbit of length delta. So I take this local unstable of a certain length and I push it forward. As I push it forward, I left out a very important hypothesis. Which is that you need transitivity. So if you assume transitivity, then as you push this forward, its iterates become dense. Okay, if I assume mixing, the iterates become dense. If I assume transitivity, the union of the iterates becomes dense. But the point is that there exists a tau such that for every pair of orbits like this, there exists a time between 0 and tau such that the teeth iterate of W delta U, whatever it does, gets close enough that it actually intersects the delta stable of X. And that's going to produce our shadowing point. So I take this intersection and I pull it back. So this point is going to be f m plus t of some point z. That point z is back here. And that's exactly the point which, when you push it forward for m iterates, lands on the unstable of u. Because it's on this unstable, it lies within delta of this orbit segment for the whole duration. And then it does whatever it does. Who cares? But within t iterates, it lands here, and then because it's on the stable, it stays close within delta, and that's your shadowing point. So I used two facts here. I used the fact that the delta stable of x lies in the Bowen ball of radius delta for every order. Okay, maybe I should work in an adapted metric in order to make this true, otherwise I should multiply by some constant. Okay, there are some technicalities. And I use the corresponding fact for the unstables going backward. Yes.
If you changed transitive to mixing this proposition,
Then you could do,
same proof you would get Bowens.
then you would get equal to tau. Yes, exactly.
So this is sort of
Yeah, exactly that.
using the same argument as Bowen would have used.
Oh yes, this is absolutely the classical argument.
I think that's exactly FT of WU then.
Yes, thank you very much. Yes, of course, the stables do not do this. Thank you. I hope that's the only problem with it. Let me just clarify. There. Okay. So in some sense, this picture is extremely important because some variant of this is the way that we are always going to get the specification property in our applications. And I want to point out the ingredients that you need here. One ingredient is that you need some kind of transitivity. You need to know that the iterates of this unstable fill up the manifold somehow. You need some kind of transitivity. You need enough control of the hyperbolicity along the orbit segments to know that this is true and that the corresponding for the unstable going backward is true. And that is only a condition that you need along the orbit segments. You don't need hyperbolicity at other times. And in fact, that's not even hyperbolicity. Suppose all I know is that the stable direction is non-expanding. Well, that's still true. So you don't actually need the stable direction to be strictly contracting. Now, there's one more piece which I didn't say yet, which is that this only tells you how to shadow two pieces. Specification says you should shadow arbitrarily many. So you should iterate this process. And of course, and the idea then is that when you iterate this process, you shadow the first two. Okay, and now you have one, and so you shadow the y, and then you shadow that. And now you have a fourth piece, x, and you shadow this guy, and then you shadow that. So you're constructing y2, y3, y4, and so on, where yi shadows the first I pieces. And of course, your errors could accumulate if you're not careful. So you need one more piece, which is that backwards uniform contraction along the unstables guarantees that the errors you accumulate here, these distances, decrease geometrically. And that gives you uniform control of the bound. I won't do the computation because it takes a little bit to write all the details. Instead, I will simply say that you need uniform contraction of F inverse along unstables. It's enough to have uniform contraction along unstables. Really all you need is that by the time you go from the end of one orbit to the end of the previous one backwards, you contracted by a definite amount. So that's actually a fairly weak condition. So let me just say uniform contraction along each good orbit segment, something like that. So I'm being a little bit vague about the exact conditions you need. Part of this is because we've never written down a general formulation of here are some general conditions which guarantee that you have specification. Because it always ends up being a little bit different in each example how we prove it for the class of orbit segments that we're interested in. Okay, so this is the idea of specification and why it holds for locally maximal hyperbolic sets. So now I should state Bowens theorem. Oh, let me bring this back down. And then I should state our theorem. So Bowens theorem, which I mentioned last time in the symbolic case, says the following. Suppose I have a compact metric space, a continuous map. Suppose it's epsilon expansive. So it's expansive at scale epsilon. And it has delta specification, meaning that the whole space of orbit segments has delta specification. Now you'll notice there are two different scales here. I said epsilon expansive and I said delta specification. So I want epsilon to be at least as big as 28 times delta. Then there exists a unique MME. The reason for this 28 has to do with various approximations that happen during the course of the proof. It doesn't show up in the symbolic case because the symbolic metric is an ultrametric, not just a metric. That's cryptic, but the scales are not so enlightening. So this is not quite the way that Bowen formulated it. Bowen formulated it saying that you're expansive at some scale and you have specification at all smaller scales. Now, in fact, if you have this property, then it guarantees specification at all smaller scales. But you don't actually need to use that in the proof. It's enough to have specification at a single scale and expansivity at a single scale, provided that the expansivity scale is just a little bit larger than the specification scale. Yes?
The definition of specification together with expansivity imply the existence of periodic points in general?
In general, I'm not sure. Maybe? I know in the symbolic setting you can do it because you can produce a synchronized word, but in the non-symbolic setting it's messier. I mean, in practice, in any of the applications, you have enough extra structure that you could actually do periodic specification and get a closing lemma. But for uniqueness, we just formulate it this way. So let me now say how I guess I have 6, 7 minutes, something like this. So let me put it all together and formulate the general result, and then next time we can talk about some applications. So what's the general result here? I promised we would weaken this. Well, what's the role of expansivity? The role of expansivity is to guarantee that these Bowen balls generate the Borel sigma algebra. And the reason you need that is that you need to be able to approximate the measure of arbitrary sets with the measure of things that you can control. But if you want to approximate the measure, you don't actually need to generate the whole Borel sigma algebra. You only need to generate it mod 0. And that's the crucial observation. You need to generate it mod 0 with respect to the measures that you care about. So let me introduce a definition and state a theorem, and then I will be done. So the definition is the following. We say that a measure, and I believe this definition actually goes back to a paper by Jerome and Todd Fisher, at least the first place that I saw it, which is that a measure is almost expansive at a certain scale if the expansivity condition is satisfied almost everywhere. The expansivity condition guarantees that Bowen balls generate the Borel sigma algebra. This condition guarantees that they generate at mod 0 with respect to mu. As long as that's true for everything which is close to being a measure of maximal entropy, then it turns out everything still works. So I make the following definition. The entropy of obstructions to expansivity, so entropy of obstructions to expansivity for the map F at scale epsilon is the supremum of the measure theoretic entropies taken over all ergodic invariant measures that are not almost expansive. And now I can, so I need that, and I need, well, so the first theorem, which I won't write down, the first generalization, is that if you replace entropy expansive with the condition that the entropy of obstructions to expansivity is smaller than the topological entropy, that's enough to make Bowen's proof go through. And that turns out to not need too much. But now I should combine these to have a general result. I should combine the way of handling obstructions to specification and the way of handling obstructions to expansivity by using the concept of a decomposition, no longer for the language, but in my dictionary for the space of orbit segments. So to do this for the space of orbit segments, I need one more definition. A decomposition of the space of orbit segments consists of the following ingredients. I need 3 collections of orbit segments. Let me allow them to be of length 0. I'm mixing notation from different papers. There we go. So just as in the language case, you want 3 collections of orbit segments, and you want 3 functions, p, g, and s, which take a given orbit segment and spit out non-negative integers. The picture is that if you have some orbit segment, you chop it up. This is fp of x, this is fp plus g of x. So this is length p, this is length g, this is length s, and the first piece of orbit segment should be in the prefix collection, the last piece should be in the suffix collection, and the middle piece should be in the good guys. So, in other words, you need p plus g plus s to be equal to n, you need xp to be a prefix, you need fpxg to be good, and you need fp plus g xs to be a suffix. So, I realize that I still have not given you any examples to indicate how you might accomplish this in any system, so for that you have to come to Friday's talk. But now I can state the theorem at least. No, I need one more definition. I need the notion of topological entropy. I've put off actually defining this thing. So, recall that a set is n delta separated if the distance between any 2 points in it is at least delta. And then we say that the entropy of a collection of orbit segments is given as follows. The entropy of a collection of orbit segments at scale delta is the exponential growth rate, as before, 1 over n log of the maximal cardinality of a set E, such that E is n delta separated, and the orbit segments of length n starting at E are all in your collection. So this is exactly what you get if you run the definition for the symbolic setting through the dictionary. Okay, now I can state the theorem. It's going to look like this. Let me leave that up there for comparison and state it here. So the general result then is that if X is a compact metric space, F is a continuous map, just as before. Suppose there exist 2 scales, epsilon, delta, related like this. Suppose that the entropy of obstructions to expansivity at scale epsilon is smaller than the topological entropy. And suppose that there exists a decomposition such that for every m. Gm has specification at scale delta. And the entropy of the obstructions is less than the topological entropy at that same scale. Then there exists a unique measure of maximal entropy. I realize I did not define what Gm is. It's the same as in the symbolic case. It's the set of all orbit segments for which the prefix and the suffix are both less than or equal to m in length. So that's the general result. And on Friday, I'll talk about some applications. Thank you.
Thank you. Any question? More?
Yes, so maybe people were confused. Yeah, maybe several people here were confused because you say that this condition that bound balls are empty, it implies that it generates a barrel sigma algebra, but a priori it's much stronger. Yes, where the condition that the bound balls generate sigma algebra is much weaker condition. So if you have this condition, weaker condition, do you have still uniqueness or not?
Sorry, if you...
Suppose you only assume that bound balls and a scale delta, infinite bound balls, the scale delta generate sigma algebra. Is it enough?
That's what you need for the proof. That's what you need for the proof of uniqueness.
Okay,
Yes.
so you don't need them to be equal to x.
Right. If you look at the proof of uniqueness, there are 4 places where expansivity is used. In each of them, it suffices to know that the Bowen balls generate their Borel sigma algebra.
Thank you again.